Okay, so in this part of the lecture, I want to think about some group G with an operation that I'll call star, and I want to pick out some single element of that group that I'll call lowercase g. One of the things I'm interested in is the behavior of individual elements under this operation. And the way I'm going to do this is by asking about their order. This is actually the same kind of order that we talked about in terms of multiplicative order for groups Z mod nz, but that idea also works for any group that you want. I'm going to use the generic language for these slides, but if it makes it easier to think about, you can pick any of these examples or even one of your own and follow along with the same idea. So you could think of 2 as an element of the integers, right, where the operation is going to be addition. You could think of 2 as an element of integers mod 10, which would be, again, operation is addition. If you want to use multiplication instead, you could think of 2 as an element. Oh, you cannot think of 2 as an element of this group because 2 does not belong to integers mod 10 cross. Maybe think of that as a 3 instead. So clearly I typed up this slide too quickly. Or you could even think of our previous example, the quaternions, and pick, say, the J element out of there and think about its order. So the technical definition is that I'm thinking about iterating my operation, whether it's plus, whether it's times, maybe it is composition of functions. There's lots of different things that my star could be. If I think about G star G star G star G star G and so on, right? Maybe this is 2 plus 2 plus 2 plus 2 plus 2. Maybe this is J times J times J times J times J. And I'm going to do that n times. There's n copies of my element. There's really only 2 possible outcomes. Eventually, for some n, this many copies of G together with themselves gives me back my identity element. So again, my E here is the identity element for my group. If my operation is addition, then this would be 0. If my operation is multiplication, this would be 1. Or it could be some other weird thing depending on what group we're looking at. Possibly, some finite number of G's gives me the identity element. If that doesn't happen, right, if I can never solve this equation, I'd say that no matter what n is, this combination of G star G star G star G star G and so on does not give me the identity element. Those are the only 2 things that can happen. Either I can find some n that the equation works, or the equation never works. So the order of my group element, lowercase g, is the smallest positive integer n, so that n copies of G together give me the identity. And that's assuming that this equation does have a solution. If no such n exists, then the order of G is going to be infinity instead, right? We're just going to define that. So this is exactly the same way that I talked about the order of an element back when we were looking at the units mod n. I'm going to keep using this order notation. If I need to specify the group that I'm using, I'll put it as a subscript. So capital G here is the group. Lowercase g is the element that I want. And the ord here stands for order. What is the order of the element lowercase g in the group capital G? And when I can get away with it, I will drop the subscript and just talk about the order of the element G, right? That'll be more helpful when we're only talking about a particular group and not talking about anything else, any other groups, because there's a lot of them. One thing to be careful about is that the order that we get depends on what our context is. We could have different sets of elements, we could have different operations, and a lot of times those different elements behave differently depending on what we're doing with them. So let me think about the element 1, right? Just the regular old integer 1. In the integers are a group under addition, and 1 has infinite order, right? No finite number of copies of the integer 1 gives me 0. But if I change my context, right, if I look at z mod 10z instead, I'm thinking of 1 as a residue mod 10. My group operation is still addition, but now I know that, well, let's see here. 1 plus 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 1, well, that makes 10, but 10 and 0 are the same residue in this group. So in z mod 10z, the number 1 has finite order. It actually has order equal to 10. And finally, let me change up my context once again. If I look to the units mod 10, and I do know that 1 is a unit mod 10, 1 is relatively prime to 10, so it's going to be one of these residues. The group operation for this set is multiplication. And I'm trying to multiply copies of 1 together until I get the identity element. The identity element for multiplication is 1. Okay then, so I need a single copy of 1 to get to 1. That means that the order of 1 is 1 under multiplication. So this is a little bit silly. In any group, the identity element is going to have order 1, and everything else is going to have order larger than 1. Okay. So we can do the same kind of reasoning that we did for modular arithmetic. How can we compare the order of an element to the size of the group, right? So Euler's theorem told us that the multiplicative order of any residue mod n has to be a divisor of phi of n. For a more general group setting, this is a special case of what's known as Lagrange's theorem. Let's say that capital G is a finite group, lowercase g is an element of G. If that's the setup you've got, then the order of G has to be an integer which divides the number of elements in the group. So if you think about the modular setting, right? The units modulo n, how many of those are there? There are phi of n. That is the definition of the Euler phi function. How many units do you have mod n? How many are relatively prime to n? Each of those has a multiplicative order, and as we've seen previously, those multiplicative orders must be divisors of phi of n. So in this setting, right, I do want G to be finite. I can't talk about divisibility if I've got infinities running around. If that's the case, then my order of the element, lowercase g, has to be a divisor of the number of elements I've got. So in particular, all of my elements here have to themselves have a finite order. In terms of my example from the first part of this lecture, let's look at the quaternion group. There are 8 total elements here, so I know that 1 is the identity element. It has order 1. There's also -1, and since -1 squared gives me 1, and minus 1 has order 2. That's the only one in this group that has order 2. And then finally, the remaining quaternions are plus minus I, plus minus j, and plus minus k, and I claim that all of those have order 4. So all of the orders that I get here are divisors of 8. Now, it's worth noting that I don't actually get an element whose order is exactly 8, right? I'm not guaranteed that by the theorem. We will dive into that a little bit more probably next Tuesday. But for now, this is where I'm going to end this portion of the lecture. The part 3 is going to be a bit of a case study again for a group that has some finite order elements and some infinite order elements.